Assalamu alaikum everyone. So my topic for today would be power systems in a steel rolling mill, AC and DC systems in specific. Now before we dive into the power systems of a steel industry, let me give you a short overview about the steel industry. To emphasize it as much as I could, I have written down the caption that the world needs steel. In the 21st century, where the world is growing exponentially, the use of steel is at its prime and is ever increasing. So, steel is the world's key industrial sector. It is a persistent process plant with high monetary use. And because of this high monetary use, it requires critical intensity organization. Now, what is critical intensity organization? For example, a steel industry cannot afford a failure of power grid or of interior power systems or of low power quality, bad choice of operating equipment, motors, gears, drives, and so on and so forth. Because all of this is contributes in making the process extremely risky, which can cause loss in production and large capital losses, which might directly affect the supply and demand chain of steel. On the right of the side of the screen, you can see the world map, which is highlighted with the increasing figures of steel, the demand in steel. As you can see, how much steel has increased over the period of 2018 to 2019, the demand for finished steel. And all of this can only be made possible through viable processes that are efficient enough, which are made efficient via incredible electric machines, which we'll look on in the upcoming slides. So, since the focus of this power system, the power system that I would be talking about is upon the steel rolling mill, so it's key. It's keen to mention what happens in a steel rolling mill. Why not are we talking about the uh, the coke broiler, the blast furnace, the steel melting shop, and why just the steel rolling mill? Well, the reason for talking about power systems in a steel rolling mill is because the other areas related to steel, such as the coke broiler, the blast furnace, the steel melting shop, they don't need any such extensive speed regulation. However, machines utilized in the finalizing mills, which is the steel rolling mill, require extensive speed regulation of keen precision. So, in the majority of the applications in a steel plant, speed was usually varied through DC machine-driven four-quadrant converters. But now, during modernization, the DC motors and drives are supplanted by AC motors and drive, which we will look on and talk about further. So, steel rolling mill process cycle. What happens here? So basically, we can divide the entire process into three areas: the roughing mill, the intermediate mill, and the finishing mill. So let me walk you through the entire process. When the steel billet is cut into fine rods and passed into the furnace, from the furnace, the steel billet comes out a red hot steel, which goes into the roughing mill, where there's an AC motor that is used on the roughing stand rolls, which smoothen and ease out the tension in the billet and make it pass through a number of set of rollers. And from there, it is carried out from the roughing mill, passed by over a conveyor belt directly into other rollers, which are operated by DC motors. Now, these DC motors throughout this part of the production line, from the roughing mill to the intermediate mill to the finishing mill, there are approximately 7 to 15 DC compound motors that are used to ensure that the red hot steel is carried properly throughout the rollers. So basically, the number 7 to 15 depends upon the size and capacity of the rolling mill. And it's not like that all of the 7 to 15 DC compound motors are operating at the same time. Rather, the number of these DC motors operating at the same time depends on the type and size of the steel that is ordered. So then from the intermediate mill to the finishing mill, and from the finishing mill, the steel is finally clipped to size and passed to the cooling bed and then to the inspection where the steel is inspected for quality, and then we get the TMT bars, rounds, CTD bar coils, and wire rods, etc. So that this is a very brief overview about what happens in a steel rolling mill. And as you can see, DC motors are present over here in the intermediate and finishing mill, while and one AC motor is present at the roughing mill. So now we'll dive into the power systems of a rolling mill. Let's talk about initially about the DC power systems in a rolling mill. There will be an overview of the operation of DC motors over there and how they are monitored. So about the overview. So numerous steel rolling mills even now lean towards variable speed and variable torque via DC machines, because DC machines are energy effective as they just require the measure of energy needed to accomplish the work. For example, a DC machine has 5,000 horsepower and just 1,000 horsepower is required to do the last pass. So the DC machine, because of being energy effective, will just utilize 1,000 horsepower. And these DC motors are compound DC motors placed at intermediate and finishing mills, as you just saw earlier in the previous slide. And these motors are started as per the star delta technique. So what is the star delta technique? In very brief words, once the motor starts, the enriching current shoots up, and at this point, the star arrangement brings down the current and puts the motor on delta arrangement, where the motor operates at maximum RPM, which it is supposed to do. Now, about the operation. So as you can see, as on the right side of the screen, there's a picture of a um, power circuit of a digital DC drive, Simoreg 6RA70, manufactured by Siemens. Now these DC motors are operated via DC drives. Let's see what do these DC drives actually do in order to make a motor work. So when there's an input supply of 11 kilovolts, it is changed over to 750 volts by utilizing the converter transformers. We have high tension circuit breakers in place to prevent voltage fluctuations, and high speed circuit breakers in place to prevent maximum overcurrent shoot. So the current feedback can be obtained by utilizing the shunt, while DC current transducer changes over AC or DC current signals into analog. Now this analog signal gives two outputs. One is sent as current feedback to the current regulator over here, and the other is sent is associated with the overcurrent tripping unit for quick overcurrent tripping. So in case there is an overcurrent, the feedback is ensures that there's the high speed circuit breakers that opens up the contacts immediately, so that the overcurrent does not affect the machine, and then the machine is not affected or harmed. And we have tachometers over here, which give out the speed feedback to the drive to ensure that the motor is following the speed that is set already in the drive. So now we'll talk about the monitoring of this digital DC. And I must add on to this as well, that once it's ensured that the speed motor is following the reference speed set in the drive, the motor starts continuing its operation at the same speed unless and until changed from the control pulpit. Now, monitoring the motor's performance. We do the monitoring via the digital DC drive. So you can see over here the Simorec 6RA70 DC Master by Siemens, which is used, which every single motor has a separate drive for it. So the drive is installed with certain fixed parameters of operation, such as armature voltage, torque, speed, and so on and so forth. So for so that data, any unintended changes, if there's any unintended change, the drive trips the motor and generates an error signal to the person monitoring it in the mill control room. So as mentioned earlier, if some parameter does not match the parameter already fed into the drive, the drive ensures that the error is generated, and the person in the control room is informed about the current discrepancy. So data received by the drive via different tangible and intangible components. So the feedback is given via different intangible and intangible components. For example, in order to monitor the motor's RPM, the drive requires an encoder to provide this data, and similarly a tachometer to provide measurement of speed when the motor will be operated above base speed or any set reference speed. So With such data, the drive makes adjustments to the operation of power components of the motor and adjusts them accordingly. Similarly, the drive controls the torque, current, armature voltage, and so on and so forth of a DC motor depending on the data received. And all of this feedback and control makes the allows the drive to make the motor's technical and mechanical control easy, automated, and efficient. Now we'll talk about AC motors in a rolling mill. So we'll talk about a synchronous AC motor, AC motors in overhead crane, and benefits of VVVFD. Now, triple VFD is something very unique, which we'll talk on in the further slides. So let's talk about a synchronous AC motor. So as you can see on the picture, in the picture on the right hand side of the screen, this is a 1500 kilowatt 3 spindle synchronous AC motor, which is installed at the roughing stand rolls at the roughing mill. Immediately, once the billet comes out of the furnace, it's red hot and it has a cuboid shape, which needs to be changed into a rod or whatever that is being required to be made. So there's already less number of tripping uh, due to overload, since capacity of the motor and its drive is very high. It's a 1500 kilowatt motor, so the tripping due to overload is pretty less. So basically, this motor rolls the red hot steel through 5 paths after coming out of the furnace. And the reason for using synchronous AC motor at this point is because of the requirement of high power and high torque, but with low and constant rolling speed. So as you can see, this is a graph of a standard synchronous motor torque speed curve. You can vary the torque as much as you want, but the speed regulation is zero because it operates at a constant speed, which, as a matter of fact, is the requirement at the roughing mill, at the roughing stand rolls of the steel rolling mill. So you can see the speed is constant here, while the torque can be varied. However, it cannot go beyond torque, pull-out torque. So this is why synchronous AC motors are used at roughing stand mills. Now, how does an AC synchronous motor work? This 1500 kilowatt beast works actually. So this where the 3 spindles are connected to this motor, as you saw in the previous image, and a liquid starter regulates the motor's RPM via resistance control. So how does this work? So when the motor starts, the liquid starter begins to sink in, and until it completely sinks in, the resistance of the motor is at its maximum, uh, and because of the maximum resistance, the RPM is at its minimum. Hence, induced torque is minimum. But once the liquid starter gets completely immersed, the resistance goes to zero and RPM reaches its maximum value, and motor starts providing the desired maximum torque. When you talk about the spindle, the 3 spindles, the top and bottom spindles spin clockwise in order to carry the red hot steel through the forward passes, while the forward rollers, while the middle spindle spins anti-clockwise in order to carry it through the backward rollers in order to smoothen out the billet. Now let's talk about overhead cranes. Now, for overhead cranes are installed in a steel rolling mill. They have essentially 3 functions: long travel, cross travel, and hoist. So they basically work on AC slip ring induction motors, which are controlled by VFDs or triple VFDs, variable voltage, variable frequency drives. They have and these cranes, these drives make a use of 4 gears that control the RPM of the motor, which hence is used to operate the crane. So when the first gear is applied, the contactors join and signal the VFD to raise the frequency to approximately 12.5 hertz, which sets up the minimum RPM. Then the second gear gets 25 hertz, the third gear gets 37.5 hertz, and the fourth gear gets maximum frequency of 50 hertz, which also gives the maximum RPM for the crane to operate at. So let's talk about the overhead crane operation via AC drives. So Trains are controlled using utilizing triple VF or VFD and a programmable regulator, which usually is a PLC. So the speed to be used as a reference set uh, is set to the speed controller unit. It is set within the drive's parameters. That is to be the speed that is to be used as reference is set within the drive parameters. The drive allows the exact placing of items. Now, how does this happen? So the drive acknowledges 0 to 10 volts as a set point for moving the motor forward or clockwise, and 0 to negative 10 volts DC for moving the motor backwards or anti-clockwise. The the tachometers or encoders are in place in connection with the motor for sending feedback of speed. So the use of these AC drives decrease in electrical energy utilization by automatic if required braking. So if only it is required to brake the system, only then the brakes are applied, not unnecessarily. And the life of the motor is also prolonged by implementing low voltage at the beginning and so reducing any sudden current surge as well. So what are the benefits of variable voltage, variable frequency drives? So as mentioned earlier, they play an important role in saving electrical power. They allow speed control that ensures that the hook of the train is positioned accurately, unlike in the previous cases when the rotor, when we used to use rotor resistance. So maintenance is easy as compared to DC drives, which are quite expensive in maintaining. They offer high starting torque. The efficiency increases when trying to resolve an error in the machine because they immediately point out the exact location where the error has occurred in the machine. So, what can we conclude from the power system about a steel rolling mill? So, we can say that we now know that a steel rolling mill comprises of high rated and high performance motors because of the degree of load they have to work upon and for the duration they have to work on them. And AC and DC drives are needed to ensure smooth operations of these AC and DC motors, and strong control is required over speed, torque, voltage, current, and safety. And these controlling drives and working motors are strong implementation of a viable power system for a steel rolling mill that can sustain a customer's quality requirements as well as meet its own capital goods side by side by making sure that has strong control over speed, torque, voltage, current, and safety, and all the parameters required to be controlled in a steel rolling mill. So that was all for today. Thank you, and I hope you enjoyed.